we need to achieve sufficient accuracy for our CPF solution. So Helm is really cool, has a lot of really cool features. First off, once we have developed the holomorphic functions, we use the pod A approximation to evaluate it for any given value of S. Second, we can analytically solve for a desired bus voltage. So say we want to determine when a certain bus is going to reach a certain voltage magnitude. We say what value of S will give us that certain magnitude, V sub C, and we're able to use this expression, which I developed, to solve for the value of S, which will give us a critical voltage. And finally, what is super useful about Helm is that if we take the numerator of the pod A approximate and we factor it, we can look at the smallest real value root of the numerator of the pod A approximation to analytically solve or estimate the point of static saddle node bifurcation. So we're able to take these equations and pull out of them when and where the system will reach bifurcation by determining how much load needs to scale to reach that point. Moving on, so I test this method on the 39 bus system in order to validate some of these results. And what I've done is I've applied kind of arbitrary loading rates, a loading rate of 1 at buses 3, 4, 7, and 8, and a negative loading rate at bus 20, so that as the holomorphic parameter is scaled, we have buses 3, 4, 7, and 8, their loads are increasing. We have bus 20, whose load is actually decreasing, and the rest of the loads are static. Similar for the reactive power injections. And I'm also plotting the active and reactive power injections at the generator buses. And what's interesting is that at bus 34, we actually see that the power injection is decreasing as the holomorphic parameter increases. And that is because bus 34 is tied to, generator bus 34 is tied to bus 20, whose load is decreasing. So its power injection is actually decreasing, which is interesting. So I also compare these CPF Helm results to Newton-Raphsa results in order to gauge the accuracy of my results, and you'll see that error is very low. The system reaches saddle node bifurcation just about at S is equal to 2. So as we approach the point of bifurcation, error starts increasing due to different numerical issues. But for the most part, Helm is a very good way to perform CPF on a small load pocket in a system. So next we ask the question, what is the probability of a bifurcation due to load buildup over a certain time period? Because this is ultimately what we want to guard against, of course. So as we're thinking about this holomorphic parameter S, which is scaling our loads, right? We want to model, which is scaling our loads accordingly. We want to model this parameter as a particle which is taking a random walk, where the t plus 1 position is equal to the tth position plus some random value, psi, where psi is normally distributed with a given mean and variance. So what we're able to go from this kind of random walk idea is we can build a concentration density function, which I introduced earlier in the presentation. And so d is a diffusion coefficient parameter. T is the length of time that we're interested in. And for a given length of time, the distribution of the parameter concentration might look something like this. And we might ask the question, okay, let's say the particle starts at 2 and it's performing a random walk. Let's say if it ever crosses the origin, the system bifurcates, or the system collapses for some reason. So what we do is we apply something called an absorbing boundary condition at the origin, and we develop a new concentration density function, or distribution, which looks something like this, as is outlined in reference 9. And using this new distribution function, we're able to calculate what's called the survival probability, which is approximately equal to the error function evaluated at the starting value divided by the square root of 4 times d, the diffusion coefficient, times t, which is the time, the amount of time in question, where obviously if t goes to infinity, the survival probability is going to go to 0, because if we're dealing with all time, eventually the system will collapse, because eventually the little particle will walk beyond the origin, so to speak. So now that we've developed this covariance matrix analytical solver, we've developed Helm, and we've developed this probabilistic framework for determining how to gauge or protect against voltage collapse, we put these together into a controller, which I'll call the statistical controller. And the process for using the statistical controller goes something like this. Number one, use Helm to perform continuation power flow on a load pocket in a system. A load pocket which has experienced poor long-term voltage stability for one reason or another. Number two, analytically estimate using the numerator of the Pade approximate the point of saddle node bifurcation. Number three, use some sort of a probabilistic framework, which I previously developed in the previous slide. Use a probabilistic framework for determining a loading stability margin based on the operator's desired probability of collapse. So maybe the operator says something like, if there is a 1% chance of voltage collapse anytime in the next 5 minutes, that is too high, we need to take mitigating control action. So we use that probabilistic framework. Next, once we've determined the proper loading margin based on that probabilistic framework, we analytically solve for the algebraic variable covariance matrix and determine what we call critical variance thresholds, which should not be passed by any bus in the pocket. So if we're monitoring the bus voltage variance and any of the buses surpass that critical variance threshold, then we know that our probabilistic framework has been violated, or our desired probability to safeguard against has been violated. And then number five, if there is a violation, a voltage violation, or a voltage variance, or a voltage magnitude violation, inject as much reactive power at the synchronous condenser bus without violating an upper bound constraint on voltage magnitude. So if there's a violation, take control action. In order to assess kind of the usefulness of this controller, we developed two other benchmark controllers. Controller number two, I'm calling it the voltage magnitude controller. Pretty much all it does, it monitors PMU data. If there's a voltage magnitude violation, such as if voltage dips too low at any single bus, we have to take mitigating control action, return to step one, continue monitoring. Controller three, I'll call localized synchronous condenser control, where pretty much this controller is not waiting for any sort of violation on the system. All this controller is doing is using an active feedback loop to continuously hold the synchronous condenser at 1 per unit at all times. So we test these different controllers on the 39 bus system, where I've edited the system slightly, and I've identified buses 3, 4, 14, 15, 16, 17, and 18 as the load pocket, or the troublesome buses, and I've added a bus 40, and at that bus I've added SC, which is a synchronous condenser, where we're able to control the reactive power injections at that bus, and I've also added, or I've drawn in a little battery, which I'll use in the second experiment, but for right now we're only considering reactive power control injection. So there are a whole lot of different test parameters that we use. You can see my thesis document for all of those. This just scratches the surface on some of them. But for load increases, as we're testing the system, pretty much the goal of the system is to see how far can each controller keep the system alive, or how far can each controller push the system until it experiences voltage collapse. So after every time demand simulation, we increase the active and the reactive power loads at the buses in the load pocket according to alpha and beta, which are normally just Gaussian random variables, with mean of 1.01 and standard deviation of 0.001. So essentially load is getting increased by about 1% after each time step, and we're going to keep iterating forward until the system collapses. So here's some preliminary results. With each controller, I ran 10 trials, and I've sorted the trials from the least successful to the most successful. Each experimental iteration took about 2 hours to run, times 10 trials, times 3 controllers, so you can do the math. And you'll see that controller 1, which is the statistical variance-based controller, is able to outform the other two pretty consistently. And you'll see that across the 10 trials, it is able to cause the aggregate apparent power load in the load pocket to increase by, on average, 58%, where controller 2, which is the mean-based controller, is only able to increase the load by about 50%, and the localized synchronous condenser controller is only allows the load to increase by about 47%. So controller 1 is shown to outperform the other two fairly well in this set of tests. I'm also presenting some of the more raw statistical data here. In this top plot, I'm plotting the average load pocket voltage for a representative trial for each controller. So we see controller 2, which is the mean-based controller, takes control action pretty consistently when it reaches some voltage magnitude violation. We're seeing controller 3, which is the localized synchronous condenser controller, is taking continuous control action, but it's clearly not taking enough control action because it's bifurcating before the other controller. In controller 1, you'll see at about 41% of load pocket increase is taking continuous control in order to safeguard the system. This next plot will summarize these results a little bit more nicely, where what I'm plotting is the probability of voltage collapse in the system using our probabilistic framework, which I've outlined, as the load level increases in the load pocket. So when we first start the trials, all of the systems are very far from voltage collapse, and it's very low probability. And then as load increases, we see that controller 1, which is our statistical controller that we've developed, does everything in its power to stay below this green line until it can do so no longer. We're seeing that controller 3 is taking continuous control action, but again, it's not taking enough control action. And again, this green line is the maximum allowable probability of voltage collapse. And so next we'll move on to considering how these statistical warning signs can be used to trigger active power control, so such as some sort of load control or distributed battery resources or demand response or something like this. So as you'll remember in my in this little drawing that I sketched up, what I've done is I've placed a battery at bus 40. So in this next experiment, what I've done is I've used controller 1. I'm using controller 1 to safeguard the system from voltage collapse. And then you'll notice that, just go back to this plot very quickly, there's a certain point where reactive power injection can no longer stabilize the system sufficiently. And so we think, okay, at that point, how about we try injecting active power using the battery resource? And so what this plot shows, or I'll start with this one, at about 41% of load increase, the system takes 3 different actions. The first action is injecting no reactive power, and we see that the probability of collapse jumps up much higher. The second action is trying to inject as much reactive power as possible, which still causes the system to be operating above the green line. And also, we try injecting reactive power, or as much active power as we possibly can, which actually stabilizes the system. And we inject as much active and reactive power as we can without violating an upper bound on voltage magnitude, which we set at 1.08, which we see both the active power and reactive power injections hit when they inject their power. So the purpose of this experiment is to show that we could potentially trigger active power resources to come online if bus voltage variance is high and bus voltage magnitude is high. Because if both of those conditions are met, reactive power injections may have diminished their usefulness. So finally, we move on and we test the controller 1 and 2, the statistical controller and the mean-based controller. We test them both on the 2383 bus Polish network. And we identify a troublesome load pocket in the southwest corner of the system. So blue buses are normal load buses, green buses are voltage-controlled generator buses, red buses are inside the troublesome load pocket, and this magenta bus, bus 2384, is a synchronous condenser bus, which I've added, which acts to provide voltage support to this load pocket. So again, what I do in this experiment is I take the system and I pushed it almost up to the point of voltage collapse, and then I started the experiment. So what we found in this trial is that you'll see that as load increases, the average voltage magnitude in the load pocket is monotonically decreasing for controller 1 because the system actually reaches a point of voltage collapse without violating any of the lower bound voltage constraints that we set on the system. So in this next plot, I'm plotting the load bus voltages of all the buses in the system. And in the top plot, this is the system under initial conditions. And in the bottom plot, this is the system just before the saddle node bifurcation occurs. And you'll see that the lowest bus voltage in the system is about just above 0.95 per unit, meaning that the system never violated voltage magnitude constraints, but it still hit a saddle node bifurcation. So this is an example where statistical control will be very useful. As we see, controller 1 is taking continuous control action to regulate voltage magnitude high, is what we found. So even though neither controller was able to keep was allowed to let the load pocket load level increase by very much. Controller 1 was about 5%, controller 2 is about 3%. The mean-based controller never took control action. So that was an interesting finding from the study. So those are the three of the experiments that we performed, and these are the summarized results. To conclude, I'll just show a picture of a circuit that I worked on last year. This is a circuit of a 100-watt AC or DC to AC power inverter circuit. And I built this after I traveled to Haiti, and I spent a little bit of time in Port-au-Prince, where the electrical grid was shut off every night for about 12 hours. When I came, and there were these inverter circuits similar to this one, I don't know how similar to this one, but that were powering the compound that we were staying at. And I just think it's a real privilege to be able to be researching electrical energy and things that really could have an impact on people's lives in the future. And I'm excited to see where some of these statistical warning signs go in the future, in hopes that they'll be implemented in order to provide safe, reliable, cheap electricity to some of the people who need it the most around the world. So with that, I'll field any questions that you might have or any concerns. Thank you very much.